Welcome back everyone. In this lecture we will see the proof of the denominator identity. First we will prove the preparatory proportion. So let me recall what it is. So we want to understand the elements of the form rho minus summation alpha alpha in omega. So the proportion tells how these elements actually behave. The first statement, so if I take W rho, so then this can be written as rho minus summation alpha, alpha comes from some omega. So this omega is indeed very explicit. So let us call it omega of W. So omega of W is those alpha positive roots such that W inverse alpha is negative root. And this is true for all W in W. The second statement, so when you take something of the form rho minus summation alpha, alpha in omega for some subset omega of this delta plus, then we can have two choices. We can say that either it is in the this reflecting hyperplane some H alpha, or it must be of the form W rho. Okay. For any subset omega of delta plus, we have either this rho minus summation alpha, alpha in omega, this is in H alpha for some alpha in delta plus, or this can be written as W rho. Okay. So this actually tells you that there are only two possibilities of this rho minus summation alpha alpha in omega. So now the third statement, which is again more important. So in case this rho minus summation alpha alpha in omega lies in the wild chamber, so then that should force that this omega is empty. Okay, rho minus summation alpha alpha in omega. So this is in the wild chamber or the fundamental chamber. So then if and only if we have omega is equal to empty. So let us prove this one by one. So these statements are very important in order to prove the denominator identity. So now let us look at the first statement. The first statement can be proved in many ways. So if you know what is the length of W, so that is same as the cardinality of this omega of W, you can use induction on that and then prove this. Okay. We are not going to see that proof. So we will actually prove straight away. So proof of 1. So one way to prove this, okay, I will just make a comment, a remark. So one can take length of W to be the cardinality of omega of W, then one can use induction on this length of W to prove the first statement. But what we are going to do, we are going to use the expression of rho very explicitly, and then we will just compute W rho using that expression. So recall, rho is given by half sum of positive roots. So in particularly if I take W rho, what will happen? So note that capital W is generated by the simple reflections Si. Okay. So capital W is generated by the simple reflections Si. So in particularly W actually permutes the set of roots. So W of delta is exactly delta. So it just permutes the set of roots. So in particularly if I take the W of rho, so then this is going to be half times summation W alpha alpha in delta plus. Now if you actually think about it, so this W alpha either it is going to be positive or negative. So depending upon that we can actually separate them. So if you just separate them, you can see that this can be written as summation plus or minus some beta, beta comes from delta plus. Okay. So, now what are all the minus terms that we have here? So, those are all the those positive roots that are sent by negative root by W inverse. Okay. So, I will leave it to you to actually check. So, now you can add and subtract rho and then see that. So, this is exactly equal to W rho equal to rho minus summation alpha, alpha comes from omega of W. Okay. So, you just add rho and then subtract rho, you collect the terms, you get this. So, this is something straightforward from the definition. So, now if we actually focus on the omega minus summation alpha, alpha and omega for general subset omega and delta plus. So, first we observe that when it actually lies in the while chamber. So, that will actually help us to prove 2. Okay. We will prove the third statement first. So, you take this omega subset of delta plus and then consider this rho minus summation alpha, alpha in omega. Let us say this lies inside C, because the converse part is clear. Whenever omega is empty, then this element is just rho, rho we know that it is already lies in the fundamental chamber. So, now if rho minus summation alpha, alpha and omega lies in C, then what it says. So, for example, we can set V to be summation alpha, alpha and omega, then it is clear that rho minus V is lies in C if and only if rho minus V, when you apply Hi, so that is going to be positive for all I in 1 to n. So, this is something we get it from the definition. So, now note that this rho minus this V of Hi, so that is supposed to be integer, because V being sum of positive roots. So, alpha of Hi is actually integer for all alpha. So, in particularly rho minus V of Hi must be integer, and this is true for all I. And not only that, we also have rho of Hi equal to 1. So, these two things are already there in our hand. So, now put them together, you can see that this implies 1 minus V of Hi is an integer, and this is actually positive integer. Okay. So, that will force that this V of Hi is indeed non-positive integer. Okay. And this is true for all I range from 1 to n. So, now, so V being sum of positive roots, you can easily see that V if you take the inner product, that is supposed to be greater than or equal to 0 for sure. So, if omega is non-empty, this must be actually greater than 0, but anyway for us it is enough to see it is greater than or equal to 0. Now, if you actually just use this information, V of Hi is non-positive integer, then by rewriting this V in terms of the simple roots, you can see that this can be written as some summation Nj alpha j, where this Nj will be non-negative integer for all j. So, if you put them together, you see, so this Vv you can compute it in two different ways. So, this Vv will be V comma summation Nj alpha j ranged from 1 to n. Then this is going to give you something greater than or equal to 0, Vv equal to summation Nj V comma alpha j, j range from 1 to n. Now, you can easily see that V of Hi is being non-positive integer. This same as saying that, so this is same as saying that V comma alpha j is indeed non-positive integer. Okay. So, if you use that, then in this thing actually becomes less than or equal to 0, because Nj's are all greater than or equal to 0 and this is less than or equal to 0, that implies this is less than or equal to 0. So, this forces that this V is 0, but we have the positive definite form. So, that forces that V must be 0, but V is 0 if and only if we know that omega must be empty set. So, this actually proves that whenever omega is in delta plus, for which rho minus summation alpha alpha in omega is in the while chamber, implies omega is empty set. So, this is just a simple calculation that uses just information about the summation alpha alpha in omega. So, now if we actually go back to the statement of 2, so that says that for given omega in delta plus, if we consider this rho minus summation alpha alpha in omega. So, we want to understand what it is actually. So, we are making actually two statements, either it is there in the reflecting hyperplane H alpha or it must be of the form W rho. So, now only two choices are there, let us say the first choice does not happen. So, assume that this is not there in H alpha for all alpha in delta. So, then that would say that rho minus summation alpha alpha in omega. So, this is supposed to be in the complement of this union of H alpha alpha in delta, but this complement it is written as union of chambers. So, in particularly this rho minus summation alpha alpha in omega must be in one of the chamber. Now, we can use the while group action because the while group acts simply transitively on the set of while chambers. So, in particularly there exists W. So, this implies there exists W in W such that W of this is inside your fundamental chamber C. And now, it is not hard to see because W again permutes the set of roots. So, you can just work it out the detail because this rho minus summation alpha alpha and omega, this can be rewritten in terms of this set of positive roots. So, if you actually rewrite that, you can easily see that this rho minus summation alpha alpha in omega. So, this can be written as, because this is rho is of sum of positive roots. So, then you are subtracting some alpha alpha in omega. So, basically you can multiply by 2 and then divide by 2. So, then you are actually subtracting some alphas and then you are actually subtracting minus 2 alpha from the summation alpha alpha and delta. So, only those things that comes from omega, they all will get negative value. So, in particularly if you actually carefully analyze this sum, this is exactly of sum of summation plus or minus alpha, alpha comes from delta plus. So, now if you apply W, what will happen? So, if you apply W on this element, then you can see that this is going to be again of times summation plus or minus alpha of W alpha alpha in delta plus. So, now W alpha is going to be either positive root or negative root. So, depending upon that, so this is going to be again some of terms of summation plus or minus beta, beta comes from delta plus. So, now again add and subtract rho, then you can see that this can be rewritten as rho minus summation some beta, beta comes from some omega dash, okay, where omega dash for some omega dash which is subset of delta plus. So, in particularly this W of rho minus summation alpha, alpha in omega is of the form rho minus summation beta, beta is in some omega dash for some subset omega dash of delta plus. So, this says that this element W of rho minus summation alpha, alpha in omega, which is same as rho minus summation beta, beta is in omega dash. So, this element is in the fundamental chamber, but we already observed that for any subset if this element is in the fundamental chamber, then the subset must be empty. So, that forces that omega dash is empty set. Because it is an empty set, you get W of rho minus summation alpha, alpha and omega is exactly equal to rho. So, now you can easily see that by applying W inverse on both sides, then rho minus summation alpha, alpha and omega is nothing but W inverse of rho. Okay. So, this proves that this rho minus summation alpha, alpha and omega, if it is not in any of the hyperplane, then it must be of the form some W inverse of rho for W in W. So, this actually completes the proof of the proposition that we wanted to prove. So, this actually analyzes the possibilities of the elements rho minus summation alpha, alpha in omega, and we are saying that this rho minus summation alpha, alpha in omega, either it lies in the reflecting hyperplane H alpha for some alpha, or otherwise it must be of the form W rho. And we also know when I apply W to rho, then it is of the form exactly rho minus summation alpha, alpha comes from this omega of W. So, this is very explicit. So, we are going to use this very explicit information. Okay. So, here I am going to leave one simple exercise for you. Okay. So, this can be proved by induction on the length. So, one can define the length of W in two different ways. Okay. So, let us take the definition that I have given. The length of W is given by this cardinality of this omega of W. So, this is the definition I am going to take. So, what is omega of W? Omega of W, those positive roots that are sent to negative roots by the action of W inverse. So, that is the definition. So, now if we take this to be the definition, then using the induction one can prove, use induction on length of W and prove that the determinant of W, which is same as the sine of W, is nothing but minus 1 power length of W. So, the determinant is given by representing each W as element of the while group W, which is subgroup of GL of E. So, sine is given by the sine of the permutation, and we are saying that is same as this minus 1 power length of W. It is a very simple exercise. If you understand the definition of omega of W, then you actually try to analyze what will happen to omega of W SI for given I. Okay. So, then you make the relation and then try to actually prove that this is what happens. Okay. So, now we have this another way of looking at this cardinality of omega of W. So, let us write that observation. So, if I define omega of W to be those positive roots such that W inverse of alpha is being negative root, then the cardinality of omega of W is what we call it length of W. Then we have that determinant of W is nothing but minus 1 power length of W. So, this is something we have it. Note that this is indeed true for simple reflection SI. So, when W equal to SI, we know that SI of delta plus difference alpha I is nothing but delta plus difference alpha I. So, in particularly, so length of SI is nothing but minus 1, which is same as the determinant of SI. So, this is the reason this is actually holding. Okay. So, now we use induction to analyze what will happen to length of WSI and then induct on the length and then try to prove this. Okay. So, now we will actually come back to the denominator identity. So, what is this whilst denominator identity says? So, let us state the result. So, whilst denominator identity or formula identity. So, this is, you can think it as happening inside Z H star. Okay. So, the identity says summation the sign of W. So, let me use this notation that we had developed. So, this actually says the sign of W e power W rho, W in W is equal to e power rho times product 1 minus e power minus alpha, alpha in delta plus. So, this is what the identity says. So, note that what we have on the left hand side, the sum side, so that is indeed skew symmetric, that means it is alternating. So, that means the right hand side also should be alternating, then you should think this as identity between these alternating elements. So, this is where it is happening. So, one can view this inside this group ring inside Z H star, where all the functions from H star to Z takes finite support. So, now so how one can actually prove this? So, we are going to use the while group action on Z H star. So, that is the key idea. So, here is the proof. So, first note that, so we have the natural action of the while group on H star. So, that is going to give you action on this Z H star. Okay. So, the elements of Z H star can be written as follows using the characteristic functions. So, this is going to be the finite sum C mu e power mu, where mu comes from some, let us say H star, where the C mu is 0 for all but finitely many mu's. Okay. So, that means you are only considering the functions which has finite supports. So, now it is easy to see that W acts on this Z H star as follows. So, you apply W on e power mu to be e power W mu. So, if you want to write it in terms of the functions, you can easily see that if I want to think f as a function from Z H star, then W f of mu is given by f of W inverse mu. Okay, this is how you define the map, because f is a function from H star to Z. Okay. So, it is okay to work with this, not a problem. So, let us actually work with this and then see what is happening. So, now what we will do, we just take this to be the sum side and then we take this to be the product side. So, this is sigma, that is the pi. So, we are going to make some observation about both of them. So, we can define this following operator. Okay, let us call it theta. So, this theta is an operator from Z H star to Z H star. So, what it does, this is the alternating operator. So, you take any f, you send it to this averaging summation sign of W, W f, where W comes from capital W. Okay. So, now it is not hard to see if I take some, let us say sigma from W. So, then if I apply this sigma theta sigma, then you get exactly this is same as the sine of sigma theta. Okay. So, this is easy to verify. So, let us verify this. So, what is theta sigma f? So, this is going to be just summation sine of w, w sigma f, w in w. So, now this is same as you can actually replace this w by now w sigma inverse. So, there is no issue. So, summation sine of w sigma inverse sigma f. So, then it again runs over w sigma inverse in w. So, note that. So, when you take w sigma inverse w in w, this is same as w, because we are working in the group. So, now using this you can see that theta sigma f is nothing but this. So, now this get cancelled. So, you get summation sine of w, because sine being the group homomorphism, this is sine of sigma inverse and then w f you get, and then w sigma inverse w you get. So, now this you can replace now by w. So, this is same as w in w sigma, which is exactly w. So, this says that theta sigma f is nothing but summation sine of w, w f, and then you get the sine of sigma inverse outside w in w. But note that sine of sigma inverse is same as sine of sigma. So, that does not change. So, then theta sigma f is nothing but sine sigma times this theta f. So, that is what we have written here. So, theta sigma is sine sigma times theta. So, this tells you that whenever you apply theta of sine sigma then sigma, so then you should get back theta, because that is going to be exactly sine sigma times theta sigma, which is nothing but sine sigma times theta. So, which is same as theta. Okay. So, now we are going to use this and then see what is going to be theta square. So, you can actually just calculate theta square and then see that. So, it is going to be exactly the cardinality of w times theta. So, I will leave it as exercise. This is a very simple exercise. So, if I compute theta square as an operator, so because theta is given by, so you can see that theta is given by summation sine w and then w. So, this is the operator. So, if you take theta square, then you can easily see that this is exactly the coordinate of w times theta. So, this is very simple identity. So, I will leave it to you to check. So, now we will actually see how this product is behaved. So, we want to say that product is also alternating, because that is what there on the left side. So, when you look at the denominator identity, so this left side is actually alternating. So, that is what we should get it on the right side as well. So, it is enough to prove it on the generators. So, which are the simple reflections. So, let us do this simple calculation. So, you start with this pi. So, recall pi is nothing but e power rho times product 1 minus e power minus alpha, alpha comes from delta plus. So, this is what we start with. So, now what I want to do, I want to apply SI and then see what happens. So, if I apply SI, so then SI of pi is going to be e power SI rho product 1 minus e power minus alpha SI alpha in delta plus. But note that SI of delta minus delta plus minus alpha I is same as delta plus minus alpha I. So, that means except alpha I, it permits all other positive roots. So, then you can write this as product of two things, then you can see that this is e power SI rho times product 1 minus e power minus alpha, alpha comes from delta plus difference alpha I, then SI of alpha I is going to be minus alpha I, SI of alpha is minus alpha I. If you use that, then this is 1 minus e power plus alpha I. But rho is nothing but what? SI of rho is rho minus alpha I. So, if you substitute here, then you get exactly e power rho minus alpha I. So, then this thing comes as it is, and then 1 minus e power alpha I will come. So, now you take this e power minus alpha I, just multiply with this term, then you get SI of pi equal to e power rho times, so this box comes as it is. So, then this is e power minus alpha I minus 1. So, if you switch this, you get the sign. So, this is minus e power rho, this box, and then 1 minus e power minus alpha I. So, which is exactly minus capital pi. So, but minus is nothing but the sign of SI. Okay. So, this is what you are getting by applying SI. Now, if I take any W in W, then W can be written as some SI1 etc. SIR. So, that implies that W pi is exactly minus 1 power length of W pi, which is same as sine of W pi, because the sine of W is same as minus 1 power this R, if this is the reduced expression, and it is not hard to see that this is same as minus 1 power length of W. Okay. So, this is something like you should check. I will leave it as exercise. This is the exercise. This is inbuilt in the exercise that sine of W is same as minus 1 power length of W. So, now we have this very interesting identity. Whenever W applied on pi, then it actually spits out this sine of W. So, that means it is alternating. Okay. So, this is one way of actually applying the W action on pi, but now we can just straight away look at what is pi and then see that what we are going to get using the definition. So, now let us straight away look at pi. So, pi is nothing but e power rho times product 1 minus e power minus alpha, alpha in delta plus. So, because this is just a product over delta plus 1 minus e power minus alpha, that is what you are taking, then if you think about it, this is just e power rho times summation. So, you run it over all possible e power minus summation alpha alpha in omega. Okay. So, maybe let me write it here. So, this is exactly equal to e power rho times minus 1 power the cardinality of omega e power minus summation alpha alpha in omega, where omega runs over all possible subsets of delta plus. Basically, omega belongs to the power set of delta plus. When omega is empty, you get that 1, and then remaining things just adds up. So, then this pi is nothing but summation minus 1 power the cardinality of omega e power rho minus summation alpha alpha in omega, where omega comes from the subset of delta plus. But we know something about these elements. Okay. These elements are going to be either of the form e power W rho for omega being omega of W, or otherwise it is going to lie in the reflecting hyperplane. So, we are going to use that and then see. So, what will happen to these elements. So, let us say if they lie in the reflecting hyperplane, what will happen. So, if you actually take that particular case, then you can see that. Okay, let us call again this as V. So, for some subset we have rho minus summation alpha alpha in omega. So, which is there in the one of the reflecting hyperplane. let us say h beta. Okay. So, suppose we have omega which is subset of delta plus, for which this v lies in the h beta. Then it is not hard to see that this theta of v must be 0, because what is theta? Theta is nothing but summation sin of w w. So, theta of v is going to be w v, where w comes from the w, but w is like v is going to lie inside h beta. So, if I take the corresponding reflection, then s beta of v is going to be v. So, it just fixes. So, then if you just multiply s beta, then what you get? So, this is something you can rewrite as summation sin of w w s beta v, where w comes from w. Okay. So, now it is easy to see that you can pair w with w s beta. So, because if you pair this, okay, you have this natural involution, okay, which is actually given by multiplying by s beta. So, from w to w you define this involution, which is given by w goes to w s beta. So, it is a natural involution, because if you compose this again, you are multiplying again by s beta, but s beta is reflection. So, s beta square is going to be identity. So, that is the map that we are considering. So, if you use this involution, then this theta of v can be written over the orbit sum. So, this is indeed best way of proving something is 0. Okay. So, we have this involution. So, let me call that involution sigma beta, which is from w to w. So, this takes w to w s beta. So, now how one can write theta of v? Theta of v can be written as summation w mod tilde, where w mod tilde is the set of orbits. So, this is the set of orbits. So, because they are set of the orbits, you can choose the representatives. So, call them w without problem. Then you get sin of w plus sin of w s beta. So, then these two coefficients will add up, because these are all the coefficients of these elements, then times w v you get, because here w v will be there, here w s beta v will be there, but s beta v fixes. So, you get w v. Okay, basically this is sin w w v plus sin w s beta w s beta v. So, that is the sum you are taking over the orbits. Okay. So, in particularly you can, this s beta v is v. So, you can just consider it as w v and it comes out. But note that this sin w is same as minus sin of w s beta is minus of sin w. So, this becomes 0. So, basically by pairing these two things, so they get cancelled each other. So, you get 0. So, theta of v becomes 0, and theta of v becomes 0 whenever this v lies in h beta. So, in particularly if I apply theta of pi, then you can see that whatever the unwanted elements, they all get 0. Okay. So, let us look at theta of pi. Then theta of pi is going to give us summation minus 1 power omega of w e power w rho, the cardinality of this, w comes from w. So, it is not hard to see that w rho equal to w dash rho will imply w equal to w dash. Okay. W rho equal to W dash rho will imply W equal to W dash. So, it is if and only if. That is because rho comes from the while chamber or the fundamental chamber. So, since rho comes from C. So, because of that, for different W's you will get different omega of W. So, you can index using that capital W, all the omega of W, no issue. So, when you apply theta of pi, you exactly get this. So, this is something you get it from observing that theta v is 0 whenever this v lies inside one of the hyperplane h beta for some beta in delta. Okay. So, now note that the length of W is same as the cardinality of omega of W. So, that implies that the minus 1 power the cardinality of omega of W is same as sine of W. So, this theta of pi is nothing but summation sine of W e power W rho, W in W. So, this is the sum sign. Okay. But we know that this theta of pi can be actually thought of in different way. So, if you actually think about it, okay, because this is sigma. So, you can actually see that theta of pi is nothing but theta applied on e power rho. Okay. So, we already have this identity, theta square is nothing but the cardinality of W times theta. So, if we use this identity, which is something we proved earlier, so that I guess gave it as exercise. So, this theta square is nothing but the cardinality of W times theta. So, if you put them together, then you see that. So, when you apply this sigma, okay, so let us do this. So, if you take theta of e power rho cardinality of W, which is same as theta square of e power rho. Okay. But theta of this e power rho is nothing but the sigma. So, you are applying again theta of sigma. Okay. So, now if you write this sigma in terms of this alternating sum, then you can see that this is exactly equal to summation sine of W theta applied on e power W rho, where W comes from W. Okay. So, one side you have, because theta of e power sigma is sigma, which is same as theta of pi. Actually, one can use theta of pi also there, not a problem, because we want to prove that sigma is same as that. Okay. Yeah. So, we do not need to apply it here, we should apply it on theta of pi. Okay. So, now okay. So, what we are going to do, so let us look at theta of pi, because theta of pi is same as this. So, theta square is same as the cardinality of W times theta, and this is true for theta itself. So, we can apply it for pi. Okay. So, the cardinality of W times theta of pi, let us look at. So, this is theta square of pi, which is theta of pi. So, which is same as theta of e power rho. Okay. So, which is going to give you exactly the cardinality of W theta of e power rho, which we have already. But what is theta of pi, which is sigma? So, here you have sigma, cardinality of sigma. So, that is fine. So, what we need to get is actually pi. We already have what is pi na? So, theta of pi we already computed. Okay, what is theta of pi? Theta of pi we already computed in two different ways. So, I guess I already told you, yeah, W of pi is nothing but sine of pi. So, using this we are supposed to compute theta of pi. So, just to use the fact that W pi is nothing but sine W pi, then using that you can easily conclude that theta of pi is nothing but summation sine W W pi W in W. So, then you get W pi is nothing but sine pi W. So, summation sine W times sine W pi W in W. So, you get exactly the cardinality of W times pi. So, this is something we already have. Okay. So, using this. So, now if you put them together, you see that already theta of pi is given by the cardinality of W times pi. Okay. So, then we do not need to worry about all this. So, this is already given by the cardinality of W times pi. So, here I am supposed to apply theta. So, this theta of pi here is supposed to be theta of this, because so we are looking at pi, which is summation minus 1 power the cardinality of omega e power rho minus summation alpha alpha in omega, where omega runs over all delta plus. Now, if I apply theta of pi, then this actually, like whenever v comes from the hyperplane, it becomes 0, or otherwise this is going to be of the form W rho. So, then this is giving me exactly summation W in W minus 1 power the cardinality of omega of W e power theta of e power W rho. Okay. So, that is the mistake that I have done. So, if you apply this theta here, then theta of pi is theta of this, but theta of W rho is nothing but sine W theta of rho. Okay. So, this inequality, this equality is not correct. So, if you just go back to this, so you already have this. Okay. So, now let us actually put them together, then you can easily see that let us do it here again. Theta of pi is nothing but theta of e power rho, because that is what this thing says. So, this is exactly equal to theta of e power rho. Okay. So, because theta of W rho again will give you this. So, but anyway, so this is exactly equal to the cardinality of W e power theta of e power rho, which is same as the cardinality of W sigma. Okay, this is something straight away you can prove, not a problem. So, now on the other hand, we have the theta of pi is nothing but the cardinality of W times pi. So, now you put them together, you can see that the cardinality of W times pi is equal to the cardinality of W times sigma. So, that will force that pi equal to sigma. Okay. So, both the side you have alternating sum. If you carefully actually use the fact that if you rewrite pi in terms of this expressions running over omega, omega comes from the delta plus, then you can easily see that only those elements that does not lie in the hyperplanes will survive, and they corresponds to this W rho. So, in particularly by applying theta, you can see that this is going to give you again sine of theta of e power rho, which give you exactly the cardinality of W times sigma. Okay. So, this is a very simple computation once we prove that proportion. Okay, I will stop here and then we will continue with the wild character formula from next class onwards. Again we have to do lots of preparation in order to prove the wild character formula. I believe it may take some like 3-4 lectures to finish the proof. So, let us actually go slowly and then try to do that. Then after that once we prove the wild character formula, so we are going to give some explicit combinatorial description of our combinatorial model for the basis of the irreducible finite dimensional representations. So, they are given by the semi standard Young tableaus. So, I will introduce all of them and then tell you like how to actually get the information about the irreducible modules from that combinatorial model. Okay, I will stop here, we will continue in the next class. Thanks.